This is problem 3-64M. Figure P3-64 shows two bars of different materials separated by 1/2 millimeter when the temperature is 20 degrees Celsius. At what temperature would they touch? By the way, this is on page 167. So go to the page, you'll have a figure there where you can see it. And one material is stainless steel, and the alloy is given there, and then brass is given also with its particular details and material designation. Let's make a note that the initial temperature is 20 degrees Celsius, and we'll find what we need along the way. So we want to find the temperature at the final state when the thickness of that gap, let's try it this way, is 0. Right now the thickness of that gap is 1/2 millimeter. So I'll use the symbol lowercase t to indicate how wide the gap is. Essentially our solution is to use the equation that materials will stretch or shrink based on a change in temperature proportional to their length and their expansion coefficient. Now, as the steel and the brass expand, they're both going to go toward each other and eventually meet and touch where the gap would be 0. So what I'm going to write here is that the deformation of the steel, the stainless steel, so the expansion of it, plus the expansion of the brass should be equal to the initial gap. Okay, so just to use symbols here, I'm just saying the steel is going to expand, the brass is going to expand, they're going to fill up that 1/2 millimeter hole basically. Now I can write the expansion of the steel with this equation, so that I need the the linear expansion coefficient for steel times the initial length of the steel. Now the initial and final length of the steel are so close to the same, it really doesn't matter, I don't have to worry about this, but technically this would be the initial length of the steel. And so then finally the delta T, final temperature less initial temperature. So this represents this first term, plus the expansion coefficient of the brass times the length of the brass, final temperature less initial temperature. And then that's the left-hand side. So the right-hand side then is the thickness of the gap initially. Okay. Now, with a little bit of algebra, you can see that we could pull out the final temperature, because notice it appears in both these terms. So we'll just write final temperature multiplied by this product plus final temperature times this product. Okay, now that's not all that's on the left-hand side. I could similarly pull out a TI, an initial temperature, times the sum of this very same product. When I did that, it would have a negative sign in front of it because both of these have a negative sign. So what I'll do is I'll pull it out and move it to the other side all in one step. Now before I move it, there's a term over here that I'll copy. So that's the initial thickness of that gap. And remember, I've got that TI times the sum, basically this term, to move to the other side. So plus initial temperature multiplied by okay, so there we go. Now, I want to divide this term on both sides so that I get the final temperature by itself. You'll notice that when I do that with the second term, all I'll have left is the initial temperature. But then, for this term, there we go. This appears in the denominator for that term. So, let's plug in the numbers and see what we get. The initial temperature was 20 degrees Celsius. The thickness of the gap was 0.305 meters. Okay, I'm going to do that because I know my lengths are in meters also. Now you have to look up the expansion coefficient for the stainless steel and the brass. To do that, that's buried in the chapter. That's in chapter 3. That's not something that's in the appendix, which may be unexpected given that there's so much stuff in the appendix. Anyway, I'll find a page number for you. This is probably a page that you would want to mark as well. And here it is, page 134. So if we look at page 134 and look for stainless steel in the alloy given, which was 430, then it looks like the coefficient of thermal expansion is 10.4 times 10 to the negative sixth. And if we look up the other material, which I think was bronze, no, it's brass, C36,000, its thermal expansion coefficient is 20.5 times 10 to the negative sixth. So we've got those two numbers from page 134. We can plug them in. Let's see, we need the steel's expansion coefficient first, 10.4 times 10 to the negative sixth, and the units are inverse degrees Celsius. And the length of the steel initially is 2.8 meters, so that takes care of this term, plus the brass's coefficient, 20.5 times 10 to the negative sixth, inverse degrees Celsius, multiplied by the length of the brass. The brass wasn't quite as long, it was 1.9 meters long. Okay, so let's see, what will go away? Well, the meters will cancel. And since Celsius is in the denominator of the denominator, it'll end up in the numerator. So we're adding Celsius to Celsius. That's a good thing. Anyway, this term is about 7 or so degrees, a little more. So 20 plus that gives us 27.35 degrees Celsius. That's the number I came up with when I saw this problem. So basically all we have to do is increase the temperature of this system by 7 degrees or so, a little more, and the two metal bars will touch.